hands. How many attended more than 2? How about 3? How about all of them? Basically, okay, that's great. Yeah, Malaga was great, and Porto was great to come back here. Well, I told George yesterday, he started putting credit to all the people who has been involved with asphalt rubber. And basically, I have to apologize ahead of time. This is in our circle in Arizona, okay? So we recognize a lot of great leaders, around the world doing some great work in asphalt rubber, advancing the technology. So I think this is what you presented. I think Doug Carlson, he just showed up here today. You showed him. But then I really added those folks, okay? Again, these are in my circle in terms of people collaborated with over some time. Angelo here, Angelo Pinto, he was here earlier. Again, great partner. We have done some work in Brazil. Shakir, you have seen him. The 2 Georges, I think they are the pillars, actually, of what we do in these conference series, and we really thank you for all the work that you have done. You deserve to be in the center of this group because of the mission that you have carried over the year. Ali Feeney, you'll see her tomorrow. She's my colleague at Arizona State. She does a lot of work with biobinders and rubber and all of that. And of course, we heard Krishna earlier. Krishna has really carried the baton in terms of asphalt rubber research and advancing the science in many different ways. And we are so happy and excited to join you in 3 years in India, to do this in India. You have to have a great program to match what the Georges they do. Half an hour, George, I'll do it, I promise. So what's the next decade? It's not going to be about proof anymore. We talked about that yesterday. Proof this and proof that and proof this. I thought we should be over this by now, right? I mean, we have established the science. We have tons of data. So it's really more about our purpose of what is the next decade going to look like. So I'm not going to go through all these points. These points were in George's slides. You're going to see them all over. But you have all these benefits have documented over and over. Having said that, I'm going to close the chapter from my side just to kind of highlight some of these initiatives that we have carried over the years and the successes we had. And that's what I mean by let us walk down the memory lane for one last time from my side. I'm not going to be talking about proofs anymore from this point forward. Friction courses, great product. Probably one of the best products we have ever had for asphalt rubber, okay? In Arizona, we put it down very thin, as you see here in the picture. I don't know if you can see the top right-hand corner. It's about 90 millimeter, okay? And this is, it went on our highway system that George Way has designed a while back and performed beautifully. So the design for these mixtures were supposed to be 10-year cycle. You come back and you resurface it. You pull it out and resurface it. Some of them actually lasted 15, and some of them are 20 years right now. They're still out there, okay? Yeah, they have some issues. They age a little bit. They have some joint separation and all of that, but they have done wonderful. Again, all the benefit in terms of splash, noise reduction, and comparing to friction courses that conventional use, they did not even last 6 or 7 years, just to give you an idea about the comparison. So that is the type of success that we have had. Now, along with these types of friction courses, they came with a lot of bonus benefits, okay? What we defined in our community, what we're talking about here is the quality of life issues, the pollutant, the tire wear emissions. We have documented that George and I were in the tunnels, just kind of evaluating and trying to get all these numbers down, all that. Exceptional performance. I mean, in terms of the amount of tire wear you get from an asphalt rubber surface versus a concrete surface in that case. Reduction in urban heat island in terms of the heat retention. One of the greatest things, I think, and I'll talk about that maybe a little bit later on, about the thermal blanket effect that layer provides as a protection to whatever is underneath it, in this case, Portland cement concrete, right? So on the bottom right-hand side, you see that when some of the strategies in Arizona kind of mixed politics in terms of what they are trying to do. So when they pulled it down, they wanted to grind the concrete. Concrete looks beautiful. This is like 30-year-old concrete pavement. And I tell you what, 2 years after that, you start seeing some cracking and corner breaks and all of that, because that layer, the very thin layer, was protecting the concrete over time. So again, I'm recapping of some of these great successes that we have had. Now we have our moderator. Sorry, Shakir, we got started. I put this slide, you have seen it, Krishna. I mean, a lot of these slides I have noticed over the year have been hijacked. I mean, to a good purpose. The people use them, and sometimes, where do they come from? Krishna Biligiri, first person ever. I still have your Excel sheet that you have done beautifully, and we use it to document CO2 emissions by using the different components of energy consumption for all the bits and pieces. So again, we win because of reduced thickness, right? We win because of extended performance in these types of analysis. So, needless to say, now, I can't imagine. We have tested every single angle, every test that you know of in pavement engineering. Guess what? Asphalt rubber has been evaluated through that test. So cannot emphasize more and more. And it passed in most of these tests. But in some places where we did not really choose the right setting to conduct that test, we had some issues, and I'll talk about a couple of those. And I'll have a small message basically to address or to give you on that one here. Okay, the proof ends of the results, binder results, even as simple as viscosity versus temperature, top left-hand corner there. Yeah, great. I mean, viscosity improvement, less susceptibility to temperature fluctuation. George showed the increased rubber content and the effect on the, what's the property there, DSR or the PG grade. I mean, it does great. At the bottom table, our experience showed that at least you get a one grade bump. Sometimes you get two, especially at the high temperature. And you get also one grade bump at the bottom of the low temperatures. So again, needless to say, we've done this over and over. A lot of you have done an outstanding job so far in documenting all of this. Now, perfecting the process is very important. And I really put this slide, and I'm going to recap it one last time. To choose the right laboratory stresses when you apply any of those tests has to be equivalent to what those pavements see in the field. A lot of these pavements are on top, open graded friction courses and gap graded, and whatever you have concrete or you have dense graded asphalt and so forth. The confinement of these top layers are so high, okay? I had a chat with Alex yesterday, talking about the SMA in his talk. Alex was saying, well, the SMA, when you go to a high temperature, if you don't have the confinement, they just collapse, which is true because you don't have any confinement. They're not designed to hold up. But because they are located on top, they always do very well because of that, reinforcement, the confinement that they have. So the message is basically you want to run a good test to get some realistic numbers, run a confined laboratory test on that. Here is an example what you see from a dynamic modulus. This is the same thing you see, modulus versus frequency. We just run it through modulus versus reduced time, so it just goes the other way. The red line is the unconfined for a gap-graded mix. Okay, very similar to the SMA that Alex mentioned yesterday. As you increase the confinement level, you can see what's happening to the modulus. You don't have to put huge amount of confinement. You can do 20 kPa, not 20 psi, 140 kPa, right? So that's what you see. You have about 70 kPa the first line. The next line you have about, I don't know if you can see the mouse here, maybe not, it's okay. 140 and then to about 210 kPa. So 20 kPa is very achievable. In the photo, bottom left, that's how we do confined tests. You put a membrane, you apply an air pressure, you make sure the inside of the specimen is drained, you get realistic results. So you get a good moduli value that you can do proper pavement design. Established a lot of models over the years. He's just one example from another great professional, Krishna's colleague, back in 2010. She's at NCAT right now, Carolina Rodesno. If you tell me what's the flow number, again, these are for gap-graded asphalt rubber mixtures. I can predict rutting performance based on the flow number, right? If you look up her dissertation, it's online, available for free. You can see a lot of these models out there. Tell me the traffic, tell me the thickness, do the test of the flow number, and you have some setting specifications, and guess what? We can evaluate the rutting or how it's going to do on rutting and so forth, okay? So, some of us, actually there are a couple. What's the other Woodstack equation, Krishna? It's not. There's a shell equation people use for dynamic modulus. So we use the Woodstack equation. Our previous mentor who passed away, but he developed a prediction model for dynamic modulus. So we can do that for gap-graded mixes. It's available out there. You don't have to do testing. You can predict what are the approximate numbers and use it for that. And again, great result. The equation has been calibrated specifically for these types of asphalt rubber mixes. And George and I, and both Georges, we work on fatigue relationships, and we have all these coefficients So when I asked that question early on for Krishna, you know, are we calibrating? So in our usage for our AASHTO software for the payment ME, we have those coefficients that we can enter to have realistic output. Otherwise, your realistic analysis is not going to be there. So we use the K1, K2, K3 for all of these rubber mixture that we have tested over the year. And the biggest slide that I have seen all the time, and I'm glad Alex is here, right? So this is a slide you have seen over and over and over. It kind of lost its track somehow, but the person who developed is right there. Alex, he's taking a photo of it right now. He spoke yesterday. So Dr. Zubrowski, back in 2007, as part of his dissertation, he must have spent a year and a half trying to figure out why the fracture model in the payment ME or the MEPG back in those days was not really working very well. In this photo, you see that the rubber mixtures have a unique behavior. They don't necessarily have the highest strength, but they have the highest post-peak residual strength, what you see in that red line above the peak, right? So the total fractured energy for these mixes are much higher, but that was not captured in any of the analysis that we have been doing back then, and maybe even nowadays. We were just discussing the other day, has it really made it to the new one or not? We don't know. And the simple math, I mean, Alex did not really have, he had to think about it for a long time. I remember he had to redesign the whole thermal fracture model in order for him trying to understand why and why not. But you see the second equation there? That's what is being used right now. That A parameter by Molinar, what that is used in the crack growth law, and I don't want to make this more scientific, a lot of equations here. That A parameter is a function of what? Of E modulus, the stress, and then another constant N in there. It has no fracture energy value whatsoever. They simplified that equation for whatever purpose and has been being used over the years, where the original equation by Shapley, it has a fracture energy parameter. So in simple terms, wasn't that simple? What Alex did, he just took that second equation, and now all of a sudden, all the predictions that we have in this payment ME were really right. So again, the message here is, let's make sure that we have confined testing, we understand what parameters we're using to document it and to relate that to the field. Okay, half an hour, so I have to go a little bit faster here. So innovate with the next generation testing. Again, there are different, it's a great test. I mean, there are great standard tests out there, but don't be afraid to try new tests. I mean, this is what we have done at ASU, and actually this is back in 2013. Very well documented by Jeff Stempihar. C-star fracture test, adopted from engineering mechanics that they use on metals, right? But we kind of converted everything and to use for asphalt mixtures. It's a simple test that helps us to understand crack propagation, how fast these cracks develop into the mixture, and the amount of energy needed to drive that crack. And guess what? Asphalt rubber mixtures have done great in this test as well, too. We use this one for fibers. I do a lot of work with fibers, and this is really a great test that we have been doing and so forth. Even moisture susceptibility test. This is a process by, he's now Dr. Atesh Nadkarni, and a lot of you here from the ASU group, you know who he is. He finished his doctorate at Texas A&M. But we developed a procedure to evaluate moisture damage, but using a modulus value, analogous to the TSR, but we called it ESR. The value is I have samples that I can do before and after, the same samples. I don't have to worry about segregation, aggregate distribution. Everything is exactly the same. You do it in the dry condition, and they do it after the moisture damage. But then what you see here, some cages and stuff, and you wonder, what the heck is this for, right? It's the same thing. We were doing gap-graded mixtures. If I don't protect those samples in the test procedure that we have to come up with this way here, they might actually change shape, deform, just because of their nature of the unconfinement. So we provided the confinement, but we wanted that moisture to go through, and that's what we have been doing in terms of evaluating moisture damage and the ESR. All right, again, a lot of that, if you search it, is, or there are some papers, publications, and reports, and so forth. How are we doing here? I think we're doing great. So the future of pavements, okay, it really had to fit in this, paradigm shift for smart, sustainable roadways, okay? And I will talk about a few of those examples and how we fit in of what we are talking about here. Climate resilience, there is no escape around it. Extreme climatic conditions going to dictate how we deal with things, how we design future pavements, right? Thinking about electric cars, how many drive electric cars here? That's it? My gosh, in Arizona now we have more. Come on, you should have more, right? It's great. So we have to integrate, how we take advantage or how we facilitate, how we integrate our designs, future designs to kind of, perhaps provide opportunities for charging stations and so forth. And then the last one here, I heard, the two Georges, and George Souza especially, with the dreaming up with the solar, powered roadways in the future. And guess not, it's not really far away. I think it's something is doable, very doable, right? So again, these technologies really will eventually help, or not help, will show us how to start thinking about roadway designs and selecting materials and so forth. So the second part of my presentation, pathways to tomorrow's innovations. Some thoughts here on this. There is no escape. We're going to be continuing to use recycled materials, like chrome rubber from tires. We're going to be continuing to use RAP, recycled asphalt pavement, regardless, right? We have to find ways how to make it work, how to put rejuvenators, how to select the proper percentages. You will see a technology from Taiwan. They use 100% RAP. Which is, has been also kind of amazing in a way. Plastics, I think Krishna talked about plastic earlier on today. So recycled materials is something we have to keep in our radar. Energy efficiency also, there's no escape around it, especially in urban-centric, infrastructure. Reduce urban heat island. In Phoenix, we estimate 40% of our landscape is roads, parking lots. And guess what? They add a lot to the heating mechanism. And it's a hot place to start with. So what type of technologies, what type of insulators, I'm hinting here, I'm going to talk about insulators later on, that can really help in the aspect of this. What about extend lifespan? And I'm not going to elaborate because maybe even I cannot elaborate on this. Look at this statement. The road of the future does not wear out, it updates. Think about a road that's not going to wear out in the future. Just kind of regenerate itself, kind of revive itself all the time. So is it possible? Yeah, possible, right? We can, technologies are out there that actually we can do that. But this is the future of how we are going to transform and design things. And then I love this, and I put this last night because I really felt that a lot of you talking about these hybrid systems, talking about this fusion of technologies. So now I'm not just only using chrome rubber, I'm using chrome rubber with some kind of warm mix additives. I'm using with some type of insulator and so forth. So I think a fusion of these technologies, Alex, I put this after I listened to Alex, perpetual designs. What did he do? He said, I have a perpetual design everybody's using, but now I'm using chrome rubber as my controlling the stiffness layer on top and the bottom. So this is a fusion of a couple of technologies. So I think it's really great, wonderful. So again, the future of the pathways for tomorrow's innovations will lie into how to utilize these types of technology in the best way possible, or call them blended tech solution like what we see here. We've done this, I don't remember, maybe 6, 7, 8 years ago. It's been a while. And now it's being used quite a bit, and Krishna talked about it a little bit. But we use RARX. Actually, I think we were helping Abu Dhabi or Dubai in a mixed design, and that's what we were doing, and we did the super pave. And so, but then we decided, you know what, we were also evaluating Zycotherm. It's a product, a war mix from India. And so we were able to use Zycotherm in a very small percentage to modify the binder and look at the mixing and the compaction temperature. They'll look like conventional, even less than conventional. So it's amazing. I think if a little video here. Nothing sticks, everything looks good. It doesn't even look hot here, but it worked beautifully. The results that we tested using those two combined technologies, they really were fantastic. If you are worried about these high temperatures, talking to Ezio this morning about overcooking binders, this will be the future of how we can take advantage of these types of technologies and so forth. I do a lot of work with fibers. I've been doing it for 20 years. I love fibers. I think it's the best modifier ever that we have, in addition to chrome rubber. But the reason I say this, it does not take much. The cost is very low comparing to everything else we have seen. And you don't have to change a mix design. You're putting some of these fibers in there in a specific way, and then you're getting a huge amount of benefits for the cost that you're putting in. We have done, I didn't find the work, I'm sorry, but we have done fibers, again, combined technologies, the fusion of technology. We have done fibers with chrome rubber asphalt. Is it cost effective? Probably yes. I mean, all the benefit you get from the chrome rubber, right? In addition from fibers. Fibers are almost like good quality controls, like a dummy-proof type of a thing. You throw them in there, they help you to control the process. Is Adrian here? Where's Andreas? Where's Andreas? Yep, you work with fibers. You know exactly what I'm talking about. And I mean, if you're talking, would love to hear what you have to say. But these are aramid fibers. You see how the strand fibrillates? I have all these branches. They really embedded into the mastic, and they provide some good benefit in there. And again, they are inexpensive, recycled aramid fibers. Aramid are the Kevlar vests that you have for bulletproof and all of that stuff, right? That's what they look like in the field. You see fibers on the shovel. You see them on the hopper. I mean, it's just all over. They go with the wrap, entry with the wrap way, and it's just really a great way to do it. This is just an example how these types of technologies can help us to expand the performance of our asphalt mixtures. What you see here is what we call the balanced mix design. Are you doing balanced mix design here in Europe? No, I mean, I know it's a big thing in the US, but I mean, to me, it's business as usual. We always did the balanced mix design. Now we have a buzzword for it, like sustainability, right? So, but anyhow, cracking resistance, you know, as I add more binder is great. That's a red line going upward. Rutting resistance, if I add more binder, is not good. So if I reduce the binder, I need to find that range where it's acceptable for both cracking and rutting, right? So the fibers in this case, and that was based on a lot of testing we have done, it kind of increases that window of opportunity for us, right? So I can be on the higher side of binder content, lower. I don't have to jeopardize the performance, but that's what these fibers are doing for me, okay? And rubber can do exactly the same thing for you. We can document it as another proof of concept, right? Again, this is some success stories of the fibers. You know, raveling and switchbacks and rutting and cracking. And I think this is an airfield in Wyoming at the bottom there. It was an open, actually, some type of an SMA mixture that also did very well. Krishna and maybe Alex and Jose, beside, oh, I've seen those over and over. Yeah, but they are great success stories, right? So I want to wrap up here with the last 10 minutes or so, maybe less. So I talked about temperature impacts. Temperature impacts on pavements are drastic. Climatic effect and all of that, you know, is not only for deformation, but thermal cracking. The huge misconception about thermal cracking, when I say thermal cracking, a lot of people think thermal cracking only takes place in very cold climates. Alex is probably one of the few people who said, no, of course, I know because I've done all this work. Where does it happen? It doesn't have to be in cold climate. It happens where you have a fluctuation of temperature. In Phoenix area, George built a parking lot for whatever experimentation you were doing at that time. It was fenced. No cars were even allowed to go in there. Did you get thermal cracking? You did. Why? Because of temperature fluctuation at higher. Going from like 35 degrees C to 45 degrees C is going to give you thermal cracking. You don't have to be at the low temperature. So again, Carlos is here. So Carlos talked yesterday. I want to expand a little bit, if I may. And we have, what kind of bird is this? Anybody knows?
Raven.
Is it raven?
Crow.
Crow. I think it's a crow. They are in Phoenix. You know the temperature in Phoenix? 46 C, 47, 40. We push 50 sometimes in the summer. They survive. How do they survive? Anybody interested? Anybody cannot, you know? So their feathers, the way they are built, they have a lot of air pockets. The air pocket is a great insulator. This is the nothing that George was talking about yesterday. Air pocket is going to give you great insulation. This is how they survive. They are black. You can argue they can absorb all that, but they do survive. A lot of studies talk about polar bears and penguins. The same thing. You know, there's a lot of inspiration of building materials for insulation, right? Same thing, same concept, maybe different type of fur on them, but the air pocketing can really help you a lot in these very extreme high temperature, low temperature. So our inspiration when we talk about aerogel is increased porosity will be the key to reduce that temperature susceptibility. This is where we started, what was it, 6, 7 years ago, Carlos, Jose? I mean, it's been a while. And I have to put this cup of coffee in here because that was George's, George Way. explanation when we have like, discussions over a couple of drinks of scotch here and there. He said, Camille, I said, yeah, I like what you're doing. It's exactly like a cup of coffee. I said, George, explain to me what's a cup of coffee. And I took that concept from him. Sorry, George, you did not patent it. But I have an espresso machine. The espresso machine, we have this much longer coffee that you get here, right? But then when it finishes, you have that foam on top. And that foam instantly is cool when it's done. Why? Because of the porosity. It's a foam. Well, the coffee at the bottom is still hot, and it can be maintained that heat if you don't touch it for a while. So, and guess what? Those friction courses, I just talked about it earlier, it's almost in the same direction of what's going on. Anybody knows the air voids in that friction course that we have, other than George, of course? What is the air voids in that asphalt on top there, on top of the concrete? 20%, right, George? 18 to 20%. This is how he designed them. That's exactly his design. The porosity there, look what's doing to the concrete. And we documented this. So the concrete, with the rubber friction course, the temperature gradients, temperature on top and the bottom, look at top and the bottom, is much less compared to the one without the friction course on top there. So that temperature reduction, temperature grade reduction is the results of that porosity of that friction course layer. Okay, and that's really great. Now, what we have done in our company, aerogel coating technologies, the inspiration again, you know, aerogel, what's aerogel? How can we use it? And Carlos did a great job talking about the history, but look at this. This is actually a blanket infused with aerogel and some other ingredients that has a fire resistance. Amazing, right? And the reason it's nothing, George, look at the complex, look at the bottom, the middle there. Look at the air void structure they have on each particle. It's very complex. When they get all that liquid out, you end up with this little voids. This is really what provides that effectiveness of insulation that you use in coats, jackets, and you know, everything else. And if I take one of these blankets and I put them in liquid nitrogen, if I put a tire in liquid nitrogen and I take it out and I try to hit it, what happens, George, to it? It shatters. Look what happened there. Still flexible. You can go to YouTube. These are not our videos. These are actually, I should have put the links, I'm sorry. But they are actually still flexible. Why? Because of the insulation that it provided. If you look at the thermal conductivity of a silica aerogel, you can even see it. It's above that red dot in 2 spots. It's like nothing, basically, right? So there is no thermal conductivity. That's what it's telling us there. So this is our, Carlos talked about the second generation of our product, which has aerogel, AMBX plus rubber. But this is our original. I'm going to go very quickly here. And actually, it has a nice little video. Let's see if I can make it run. Why not? So, I mean, here is the rubber alone, and I'll come back, and I think we'll show you just a final image. A conventional binder, SBS binder, rubber binder, and then the aerogel binder. Last one standing. Of course, it melts eventually, but for the duration that we do. And this is a brilliant test that Carlos developed to evaluate thermal susceptibility. So now we use this as a quality control for our product. When it comes in, you know, what works, what doesn't work. So again, amazing insulative properties. Little scientific fact how things develop in terms of thermal cracking. This is an equation showing the thermal stress developed in pavements and material as a function of alpha, expansion contraction coefficient, plus the stiffness of the material with that temperature range we're talking about here. If I want to reduce that stress, thermal stress, what do I have to reduce here? I can play around. If I can reduce my delta T, I can win. If I can reduce my alpha, I can win, right? I mean, again, for our temperature range. So if I have a huge gradient, I have small gradients. And that's exactly what we are doing. I mean, look at this again, you have a patent on this too? Not this one? Okay. Anyhow, this is a test that a sample sits on a frictionless surface, and then he cycles the temperature from 60 degrees C or 50 degrees C to -20 and up and down, all that. But again, the message is look at the thermal coefficient of expansion. I had 10% aerogel AMBX reduced to almost less than half, and then if I add 20%, almost 0.08, which is like nothing. In fact, if you look at the changes here, the amount of strain developed in the specimen, we measure it as it cycles as a function of time or temperature. Here is a conventional asphalt in the black. I don't see my line there. Let's see, I should be doing here. This is the conventional asphalt. Here is one treatment, and here's a 20% that was in previous table, almost like a flat line. The mix becomes insensitive to temperature fluctuation. I mean, that is the goal obviously, if you put too much of this aerogel, the material becomes brittle, more weak, right? So this is where the rubber comes in to help that or to optimize design. Done a lot of test sections. This is what Carlos talked about. So our second generation project, we use the RAC, which is rubberized aerogel composite. Again, we take advantage of the chrome rubber with the aerogel to produce a super duper mix that can perform in a beautiful way. And I'll throw that out there. We have used technologies. I mean, Doug Carlson is out there, the Smart Mix, the RARX, and all of that. Can really help to fill in that gap for us in here. This is the test, actually. I don't think you showed this one, Carlos, but on top, after the samples are sitting there, the rack, look at the rack, how it sits. Here are the chrome rubber alone, actually doing better than the control, and this is only the AMBX. So it's really a great way to optimize to come up with that proportion. And I think you showed the Hamburg, which has also a great way. Couple more slides, and I think I'll be just actually before my half an hour, my reduced time here. Be on the lookout for this technology. So again, we talk about this new concept, the new ideas, right? So HKT, they have a booth out there. Is Tony here or no? They are sitting at the booth. So I mean, they use a resin modifier to use 100% wrap to have a cold mix. All these pictures taken by me. I went to Taiwan. I was watching the process. Okay, how it's produced at the plant, how it's being placed, how it's being compacted. And then this guy in front of me taking, look at this, 33 degrees C. That's the temperature of the mix that's going down and compacted. So they have a problem with the aggregates, so they try to use 100% wrap. And then they start adding rubber to it. And that's why they are here. I mean, this chrome rubber to this types of technology, again, the fusion of these technologies are actually, some of those features. So okay, Tony and his co-inventor are sitting on a little section they built for their trucks, asphalt in and out all the time. And it just, I was kind of amazed. And I know there's a lot of product out there, but they have a highway section that has been put out there for the last 2 to 3 years. They have typhoons, or hurricanes in the US we call them, excessive amount of moisture rain, and it's doing great. So I've never seen anything like that in my life. Okay, final thoughts. I hope we agree. We don't need proofs anymore. Okay, I think let's put that to the side. And let's look for new ambition, new directions, new thoughts. I mean, policy, obviously, is our bottleneck. It's not the performance anymore, right? We talked about this. And this is something, maybe some of these thoughts could be for tomorrow's panel discussions, and maybe you want to tack some of those and just kind of expand on them. So we overflew the technology, but we are maybe under-communicated its value, especially with policymakers. And I think this is really where we face our biggest problems nowadays. I put this after I listened to George Way yesterday. I think, yes, AI, we do everything in AI nowadays. Imagine AI-assisted mix design and predictive modeling. Imagine you don't have to do anything in the lab. You just do everything by an AI algorithm. Would that be acceptable to you as a designer? Would you be comfortable? Why not? We can train these models. We have the information. We have the technology. So performance-based specification with real-time feedback loops and all of that, just simulations. We don't really have to spend maybe more time in the lab if we have all the right component in there. We have to close the loop on this circular economy. I think Alex did a great job talking about it, but the carbon valuation, we have EPDs, we have EPDs, what's the environmental product declaration, and this is something big, but they document products have to document their value, their CO2 footprint, their life cycle assessment, and so forth. So I think this is really something we probably can build more on it, and again, instead of focusing on chrome rubber is really doing great. It's doing great. We don't really need those proofs anymore. And I'll put this one here. Maybe it's worth a discussion by itself. So maybe, and I know it's not, because we have technology nowadays. So I don't think the next revolution, what we do in our scientific community, it's not going to be the materials. Materials are there already. But it's really the mindset. Okay? It's how we perceive things. It's how we accept change, of how we accept bad experiments and learn from them and build new ones. So I think this is really, as my advice for us, for the community, for what to take from all of this is to how we can go in that direction than just putting a couple of comparisons and saying yes and no. Everybody's doing a great job. Don't take that as a negative way. I love what I heard from everybody so far, and I love what I'm going to hear tomorrow as well. But I think this is the direction that we perhaps in 3 years we can report on at the next conference. So with that, Mr. Chairman, I'm done. Thank you.
I have a question for you.
Yes, sir. The mic is not on for people. Push it, just push the button, yeah.
So basically what you described is a thermal fatigue phenomena. It's a cyclic, based on the cyclic stresses due to temperature variations.
Yeah.
And by using the aerogel, you're reducing the strains in the material because you're lowering the temperature, basically. You're insulating the temperature. Therefore, you have a thermal fatigue, longer fatigue life.
Not necessarily lowering the temperature. I am reducing the temperature fluctuation. So, so the temperature might stay at a certain value depending on thick versus thin designs, and we have different scenarios how to do things. But I'll give you, for example, the concrete and the porous asphalt on top. What we have found that the concrete, for example, the temperature, average temperature stays higher than typical without the cover. But the temperature differential from top to bottom is reduced, and that's what we are after. How to reduce the temperature changes in the layer in order to minimize the thermal stress you just talked about. So absolutely, it's a thermal fatigue stress, but we kind of shield it from that. And the way to do this is by designing a certain amount of particles in there to achieve that.
Yes, thank you. Go ahead.
Here comes trouble. Yeah.
So it's very interesting technology. So congratulations.
Thank you.
With a new idea, it's great to see new ideas in the industry. How do you feel when you look at this product with ages? Like, I mean, you live in a very extreme location for the aging of materials. You know, if you say 1 year, 2 years, 3 years, 5 years aging of material, how do you feel it might be performed?
So we don't have a lot of data on aging yet. This is coming. But anytime you reduce thermal stress, you would expect, logically, to have less aging compared to a conventional mix. If I can shield my pavement if I can shield it completely, I look at extremes usually to the way I think. If I can shield temperature from a pavement, there's no aging going to take place, or minimal aging going to take place.
Now you had that great slide with the flamethrower on the pavement. If you look,
Not pavement. It wasn't pavement, yeah.
If you put that on the pavement, do you think you can go through many cycles?
A very good question. We are currently, in fact, Carlos will be speaking in November at our conference about fire resistance pavements. So we believe, we haven't done a lot of work in this area, but these particles will serve toward that goal, okay? They might not be completely fireproof, but they will help to reduce, for example, our thought, if we use our product, in areas, in Arizona, we have a lot of fires during a certain season. So if we can put our product in those areas that we know we have potentially for fires going to sweep through the roadway, we will give a chance for people to travel these roadways before they completely disappear, basically, or melt out, right? So we feel that we can provide that protection with these particles, yes, but we don't really have all the data to document it yet.
Fire retardant materials are actually quite important in the asphalt space in certain markets. So thank you very much.
Thank you. Thank you. Appreciate it.
Go ahead.
Two questions. One question, can we, when we're adding the rubber product, can we see some reduction of bitumen?
When you use the combined technologies, when you use the rack, rubber and aerogel, or no?
Yeah. For example, or
No, I think the idea is our particles, in fact, they will have additional binder anyhow because they are pre-coated. So they will add, I mean, might have an option to reduce some of the binder content, but it doesn't affect it this way, Carlos? Okay, so yeah, I would say that doesn't.
the question about this signal, very small layer of asphalt, what you remove the concrete.
Mm-hmm.
How is the connection between and the thermal cracks? You are cutting it, this on the thermal cracks, or what is?
So the resiliency, like George Souza explained, this 5 times the resiliency with the rubber, so that you get the benefit there. So any joints or potential cracks in the pavement does not really reflect through. It's kind of hardly. Now, if they do, they are much reduced width comparing to conventional mixes. We have seen that, right? But again, this is a friction coarse layer. It's not intended to be an interceptor to any major cracks or any joint movements. So if you just accept that, more of a thermal blanket, friction, splash resistance, and so forth, its function is designed for other benefit, but not necessarily to solve some major joint issues that you might have. I think we apply a tack coat. We apply a tack coat before you put it down, and this is how you bond it. So it's just like a regular tack coat that you put in. No SAMI, no. This is the friction course, no SAMI, yeah. When we do actually a gap-graded mix, actually the one in Jakarta that George Souza showed, he used a SAMI, and then he put the gap grade and he put the friction course on top. So in that case, yes, because it was more of structural sealing and adding more benefit. But in our case, we were looking for these other benefits, but not necessarily the structural capacity and so forth.
It looks like George ran out of chocolate today. He's not distributing chocolate.
He has a lot of chocolates, yeah.
Oh, there is? Okay, well, yeah, go ahead.
Do we have time for another one?
I think so.
Thank you for a very nice presentation. I think the last slide here was a very interesting conclusion about the communication. But I think the research going forward is also important, but I think that maybe we should also shift our focus into how to actually communicate and sell, and how to penetrate the layer of denial and ignorance that we still see out there in some markets. So maybe to advocate for future topics on this conference, we would also attract more people, other people.
Thank you. I think it's really, yeah, thank you. Thank you for feedback. It's like in politics. This slide can go for politics as well, too, right? I mean, it's the same thing. I mean, what we do in our community is, so yeah, thank you. Appreciate that comment, yeah.
Thank you. Any other questions? Go ahead, George.
Just to further the concept that you just presented, not here, Pratt is a Portuguese expert on this. He was a chief pavement engineer in Portugal, and he just texted me this morning. There's nothing else to prove. It's just need to inform. And he's proposing that we go around the country to all the places and just present, because information is not out there for some of the key people that make decisions. So it's just
Interesting, yes, I agree.
Have that heart for accept change and accept, new things. And but that's our mission, I think, for the future, is how we can get through to people. But we can do it, because it can be done. We just need to focus more on it. Thank you.
Thank you.
Let me go.
Nice job, thank you. Our next speaker, I don't see her. Antoni's evaluation of sustainable pavement construction and maintenance using multi-recycled RAR mixtures.
Hello, good afternoon. I will present an evaluation of sustainable pavement construction and maintenance using multi-recycled RAR mixtures. Well, as we know, the transportation infrastructure is very important for the society. I don't know, previously this happened with the other presenter. I will stop.
VI.
Oh, okay. Every slides.
You can turn off the time slide.
I'll try. Okay. I think now it's okay. No. I don't know what's happening. Oh.
Are we having technical issues?
Because he's fixing the advanced slide after some time. I will try again. I turn off the function, but I don't know what's happening. Now it's okay.
That works.
Sorry. Sorry for that, but the PowerPoint is assuming the past the slides after some time. Well, as we know, as I'm saying, as we know, the road networks are very important for societies, for the countries, for the developing. We know that. It's true for everyone in every place of the world. In 2022, only USA and Europe produced around 680 million tons of bituminous mixtures. It's a huge number. Only these two continents. We know that, and we are talking about pavements, and the pavements need to be maintained or rehabilitated after some time. And for this, we need to replace or substitute the layers, namely the surface course. Well, and with these maintenance actions and rehabilitation, we produce RAP. RAP is a material that comes from the old pavements, as everybody knows, in this room, of course. And this is an excellent material. We have aggregates and we have bitumen. We have the two raw materials to produce bituminous mixtures. And to shift to a circular economy, we need to use that. Use that material, and with this material we can have a sustainable pavement management. And to assess this, we can perform some life cycle assessment to quantify the environmental impact, but it's important also to quantify the sustainability at all, considering the economic impact, the social impact, and the environmental impact. The LCA is a standardized method and allows us to perform a fair comparison between some scenarios, the scenarios that we want to analyze. In our case, we define the functional unit that is 1 kilometer road from Portuguese road network. It's a 2-lane road sections with 7 meters width, and we analyze over a period of 36 years. We have two scenarios. The scenario A, that is the real scenario, the scenario that was real performed, the milings and the rehabilitations that was real performed, and the scenario B. The scenario B is the same scenario, but the sustainable one, using some amounts of RAP. We define 25, 50, 75, and 100% of RAP by performing hot mix recycling. We have these structures, and we have the different layers and the milling actions at year 16 and at year 33. For the second milling, we considered that we use the previous mixer with RAP. And because of that, we are talking about multi-recycling, recycling several times the mixers, of course, using rejuvenators. To perform the analysis, we use the CIMAPRO software, combined with EcoInvent database, and some consultation of Portuguese paving industry to complement some variables with the real data from Portugal. To access the impact categories, we use the endpoint normalization and the midpoint impact categories using the impact 2002 plus method. And we have 15 characterization factors and 4 damage categories. And the results are clear. We have an increase of sustainability when we put more RAP. If you use more RAP, we have an increase. It's like a linear relation. Of course, we are not reducing all, because transportations are the same. We have the construction and maintenance actions, but we are reducing a lot. Of course, the factor that we reduce most is the mineral extraction, the extraction of raw materials. But we are reducing also transportation and the energy consumption, because we are using RAP, that is a material that have our 2 raw materials. For 100% of RAP, we can achieve, in terms of average values, an average of reduction of 40%. For 25% incorporation, we reduce, considering the baseline scenario, around 20% in terms of average value for the 15 impact factors. If we combine the 15 impact factors in 4 damage factors, this is a grouping of the 15 characterization factors in these 4 damage categories. We can see that the resources are the damage category that reduce the most, because we are reducing the extraction of all petrol and aggregates. Of course, we have another impact in terms of human health, in terms of ecosystem quality, and the important one also, the climate change. This represents a significant reduction in terms of virgin materials consumption, because we are using a material that allows us to reduce the amount of material that we need to extract from the nature. We have a reduction also in terms of environmental footprint, because we are reducing the transportations, and we are the process associated to the processing of RAP to incorporate in these new bituminous mixtures are very small, because we are talking about some grading and crushing only, and we are reducing the transport as we have material closer to the asphalt plant. The multi-recycling improves this reduction in terms of impact factors from the virgin material reduction and the other less transportation and improve energy efficiency. And we improve also, they are all connected, we improve also the energy needs, because we are reducing transportation, we are reducing the extraction of raw materials, and we are reducing the actions to produce bituminous mixtures, as we can also incorporate, for example, warm mix asphalt to produce this type of mixtures. As conclusions, I think it's clear that incorporation of RAP, namely when we are considering multi-recycling capacity, reduce significantly the environmental impacts. Of course, if we reduce more RAP, we are having better results in terms of environmental impacts. They are connected. And we have considerable impacts in terms of natural resources exploitation. And considering only the environmental point of view, the 100% of incorporation of RAP is the best solution. This allows us to have a real circular economy. As future directions, it's important to implement this methodology considering different geographic and project conditions. Of course, each project needs to have an analysis if it's viable or not. For some projects, these results can be quite different because we can have a high reduction in terms of transportation. For example, places where we don't have good aggregates, for example. We need to integrate this LCA in a broader point of view, and in our analysis we need to consider economic factors and also social and structural factors. In this case, we considered the same periods in terms of replacement layers as we analyzed the mechanical response of this type of mixers, and they perform more or equal better than the previous mixer, the mixers with new aggregates and new bitumen. The mechanical behavior and functional behavior are more or less the same, in some properties greater than the traditional mixers. And of course, it's important to extend this research to the rubberized asphalt mixers. It's important to look if it's possible to multi-recycle this type of asphalt rubber mixtures or RAR mixtures. It's very important to look at it because we need to look for the future. We need to look if it's possible multi-recycle this mixer to don't put a problem in the future, to have solutions for the next 20, 50 years, for the next generations. And that's all. Thank you.
Thank you. Anybody with questions?
Okay.
So you're recommending 100% recycle?
Yes.
RAP. And how do you overcome the aged binder in the 100% RAP?
We need to look at the use of rejuvenators, of course. It's very important to rejuvenate the properties of the binders. But we cannot use softeners. That is quite different than the rejuvenator, because some rejuvenators are not real rejuvenators, are softeners of the binder. And we need to take care of it when we analyze the performance of the mixers.
Yes. Thank you.
Okay, thank you.
There's another question here. Go ahead.
I'll just mention that we've developed a very quick way of looking at rejuvenators. We can do a 10-minute DSR test, calculate the logical index, and the Glover-Rowe parameter tells you what you need to know about the performance of a rejuvenator. So it's a very quick way of trying to do this.
Yes, thank you. Thank you for the comment. Okay. Thank you.
Any other question? Thank you. Okay, so our next speaker is MCall, completion of the first DAP for used tire powder and digested and concentrated rubber bitumen granulated RAR X.
Good afternoon, everyone. First, I would like to express my gratitude for the opportunity to present the work or RAR 2025, and to Dr. Souza for his outstanding work in organizing this event. Especial thanks ao Laboratório Nacional de Engenharia Civil, que está sempre ao serviço do conhecimento e da sociedade. My work is focused in sustainability, especially the optimization of asphalt rubber used in Brazil through the application of a correct asphalt rubber binder content in paving projects. In Brazil, we employ the batch production models, terminal blend. This study presents a method for calculating the correction factor, which helps optimize the use of asphalt binder in the field, improving the production process by ensuring proper regulation and agitation and asphalt rubber in storage tanks. Brazil is a continental size country with an area of 8.5 million square kilometers, and that more than 1.75 million kilometers of roads, of which only 11.5% are paved. Therefore, Brazil still has approximately 1.35 million kilometers of roads that need to be paved. The Brazil transportation system is predominantly road-based, with about 65% of cargo and more than 95% populations traveling through the highway network. Brazil is approximately 125 million vehicles. Each year, around 450 million tons of scarce types are discarded, equivalent to about 90 million individual units. It's a big country. CONAMA resolution requires the collection and proper disposal of used tires, establishing a ratio of 1 recycled tire of every near-tired word. Pavement chains in Brazil. This is more than 90% of asphalt used in Brazil is produced by Petrobras, the company responsible for manufacturing asphalt cement. Asphalt in Brazil is still classified according to penetration test, and two main grades are commonly used: natural AC 5070 and AC 1345. The country is currently in a transition phase toward the performance grade PG classification system, which is expected to be fully adopted soon. The distributors of asphalt cement is carried out by transportation companies using their tank trucks. These trucks collect the asphalt cement directly from Petrobras, this refinery. Part of it is delivered to hot mix asphalt plants, while another portion goes to asphalt distributors. The distributors modify the asphalt cement, produce and marketing asphalt emulsion, and modify asphalt with polymers, SBS, and crumb rubber. In Brazil, asphalt rubber is produced through a batch process known as terminal blend. The material is produced, stored, then later transported to the hot mix asphalt plants. The continuous production process and dry process rubber additional in the hot mix are not used in the country. We also know that asphalt rubber contributes to sustainability by removing scrap tires from the environment, leading to more durable, cost-effective, and environmentally friendly pavements. Therefore, it's important to establish the methodology to evaluation the sustainability of asphalt rubber in trichloroethylene, the most used solvent in Brazil. This allows for proper assessment of storage and handling conditions of asphalt rubber is customer thanks, as each production to storage process might have its own characteristics. It's ISTM 6114, it's the base. Asphalt rubber is defined of ISTM as composition of asphalt cement, good tire rubber, and additives. Contains in minimal 15% rubber in total weight of the mixture. It's crumb rubber, it's 2 machines. In the production of asphalt rubber for this study, 2 types of wire mixes were used. The low shear mixes was employed only for the dispersion and swelling in the ground tire rubber, while the high shear mixer was used to extract the polymer components present in the tire. The portion of the tire utilized is thread layer, which contains the highest concentration of polymers. Now, we can observe all the constituents of crumb rubber. To produce this material, it's essential that rubber powder exhibits a high level and purity. I must be free from steel and nylon, and we have control particle sizzle distribution. The polymer is the key element in this study. It's known that truck tire produce higher quality crumb rubber compared to passenger cars tires. Therefore, the greater the proportion of truck tire rubber used in the blend, the better than performance of the result asphalt rubber. Carbon black plays a critical role as a reinforcing agent, increasing the stiffness of the material. It is insoluble in both water and asphalt and serves as the main antioxidant. Moreover, sulfur vulcanization enhances the strength and elasticity of the rubber. Properties are transferred to asphalt rubber binder. Asphalt characterization. The asphalt used in this study was asphalt cement grade 1517. The chemical balance of the base binder was monitored by measuring the proportion of saturated asphaltanes, maltanes, and resins. This process is extremely important because crumb rubber tends to chemically unbalance the asphalt binder composition. Therefore, it is necessary to adjust the formulation of the asphalt cement using rejuvenation agents to restore the proper chemicals equilibrium and ensure consistency and performance. The different types of crumb rubber were analyzed in order to determine which sample would be most suitable for the study. The sample with the highest degrees or purity was selected for further testing. The study focused on the wet process methodology, which involves the dispersion of solid particles into a liquid and high temperature, followed by high shear mixer. The process time for sample production was 4 hours. Presented here are some of the results obtained after the dispersion and high shear mixes stages. The dispersal and solubilization of rubber in the asphalt binder were observed through several behavior changes, including as an increase in softening point, a reduction in the penetration, and an improvement in the elastic recovery of the binder. The study focused on crumb rubber type 1, which exhibit greater elastic recovery and high polymer content compared to the other samples. The penetration volume decreased, while both the softening point and dynamic viscosity increased, reaching nearly 2,000 CP. The most effective product method to qualify the insoluble material in the Soxhlet extraction technique, which allows for the use of a substantial sample mass. The insoluble fraction mainly consists of carbon black, metals, and fibers present in the crumb rubber. The binder achieved a high performance grade PG76 and high temperature. The solubility in trichloroethylene resulted in a correction factor of approximately 1.808. Laboratory test is the machines. Here are the laboratory instruments used in the study. The rolling thin film oven, which simulate short-term aging, the dynamic shear rheometer, DSR, and solubility in trichloroethylene apparatus. The calculation of a correction factor, since a portion of the rubber is insoluble, the solubility of asphalt rubber and trichloroethylene in less than 100%. For a formulation containing 17 crumb rubber and 83% asphalt cement, 50-70. The insolubility fraction on the crumb rubber was 50.1, while the solubility factor is 18.31. The correction factor determined its formulation is 11.9%, meaning that the final extraction residue must multiply it by 1.08. Applied, this correction factor is essential to optimizing to use the asphalt binder and prevent field issues such as blending, binder, exudation. These results were confirmed by the thermogravimetric analysis, TJA test. Test 1 for asphalt cement, test 2 for crumb rubber. And in conclusion, the Soxhlet extraction method is effective to determine the insoluble content in rubberized asphalt samples. The solubility in trichloroethylene is directly related to the purity of the crumb rubber, influenced by carbon black, metals, and textile fibers. It is recommended to perform a test during production and storage, with continuous recirculation and agitation to ensure the proper rubber's dispersion. Sampling products should be standardized and Soxhlet solubility tests used to compare results and ensure products homogeneity. It's essential to monitor the quality of rubber. The resilience test indicates rubber quality. High resilience means better elastic recovery and rubberized asphalt. Okay?
Thank you.
Any questions for me email?
No question? Yeah, go ahead. Give me. Yeah. It's Camille.
Okay. Presentation, I just want to know the... Can I get chocolate now?
And Angelo Pinto. Introduce George Souza for you guys.
PGA analysis, all that. What's the difference between all that?
Hi, Angelo.
George Souza presentation.
Presentation, okay, by George.
May I?
Go ahead.
Hello, I'm presenting this on behalf of, no, not this one.
Angelo Pinto.
What is the presentation name? 15, 14? It's not here today. Fernanda. Acho? Não está cá nenhuma para 16. Já está, sim. Okay. Já encontrei. So, I'll be making the presentation on behalf of the Brazilian team, and the story is another confirmation of what we already know. I'll try to be very quick. These are the participants that have been involved in making this road. This was 15 years ago. These were the pavement condition. And at the time, we presented the normal solution. What to do in a pavement under these conditions was the conventional solution on the left. You remove everything, recycle the pavement, 25 centimeters of crushed stone, and hot mix. This was the standard in Brazil. Well, we proposed just don't touch the existing pavement. Please don't touch the existing pavement. It's suffering there for 500 years. Leave it. Just put something good on top of it, okay? So we left it. We made a little leveling course, gap grade and open grade. This was done via wet method 15 years ago, pure traditional technology from Arizona and California. Actually, this is a picture, you know. Leveling course a little bit, existing pavement, the gap grade, and the open grade on top. At the time, there was the need to check several quarries because they were actually different, and the problem was the LA abrasion was not as demanding as what we wanted. We had to compromise, and there was the first time we did open grade, at least in that region, and they didn't know what to do with the fines. So the quality, the mountains of fines where they're producing the normal mix that we want on an open grade. This is going to be interesting later. So, how is the pavement today? So they just run falling weight very recently, and ta-da! The pavement is better. The pavement now is improved the deflections over time. When it was done, we did falling weight, and now over time has improved. My understanding, to think about this, is that this pavement now has prevented water from going in, and in time the base is getting stronger. This is me understanding. How can this happen? But it's a fact. The falling weight now is average deflection is 35, 0.01 millimeters, and before was 55. This is remarkable, meaning the pavement is improving the structure because of the solution we applied.
Same amount of testing?
The same?
Same period of testing?
Yeah, same thing, same time, yes. So another interesting, this is one direction, and the other direction, it's slightly different, but still the same benefit of improving this. Now, another, the average of all these things, here it is, and it's a very good reduction. Now, an interesting thing here, this is different. We didn't have the results now, but the skid resistance of this road now is better than the skid resistance of nearby roads that were made recently. So this means that the structure, the aggregates, what we did that on open grade is better than the standard demands that they have now on the roads that they made. I think this is very significant. So this was me and George Way many years ago, and at the time this is one concern, that the curves were slow and turning with the big trucks. We're not so comfortable that they're going to use it there well, this open grade, because we know open grades are usually used in normal flow traffic. And also, I was worried about the very high LA abrasion on these aggregates, okay? But, let's try it. This is an experiment. Let's see what happens. Now, an interesting part that I also have to tell you is that during the day, they were construction day and night. During the day, I would go there and I would see these mountains of fine particles, what was left over from segregating the material. Because I was there, no, I want rocks. I don't want rocks and dust. In the morning, I get there, the dust disappears. So later, I found out that it was a little random, this gradation is was open and semi-open because they wanted to get rid of the dust. Interesting, we learned something. The pavement is all in great condition, except in the turns. And on the outside turn, there was some ruts, okay? And some think this is because of the open grade. Now, I think this is because of the fines and of the low or high LA abrasion. But the fact is, they replaced these little sections only on very specific curves, okay, with gap grade, and after that, everything is perfect. So I'm just showing you that we must follow specifications, okay? That's why they exist. When you have a demand for LA abrasion I don't know, 15, and they give you 45, you must expect some differences, okay? I like to be transparent and present the good and the bad, and out of this project that performed fantastic, except these little curves where we had to replace the gap, the open for the gap. And Angelo, you want to say something?
Okay, so it's all right.
Okay, you agree? Yeah, he agrees. So he was the boss that at the time was at as the president of DNER, and is the one that made the arrangements to make this 33-kilometer road with asphalt rubber, and everything else is performing perfectly, okay? I just like to show and put the finger and remind you, we have specifications, kind of, for some reason, you know, it's fair to try to improve it, but, you know, you can find some consequences, okay? So, now the new boss is David Perini Vermelho. He's the president of EMR, and he likes very much this soccer team. Any questions?
George?
Yes.
Moisture have to do something with that failure, the localized failure there, like where the accumulation of moisture?
No, for me, it has to do with the rut resistance. You see the shape? You see the shape? You see the...
Yeah, but that sketch, but I can't tell from the photo, it's really drainage because I see the high grass and...
No, here, no, the drainage is okay. They fixed the drainage. This is on the top side of the curve, always on the outside turning. So this is a rutting, let's say, what's called a rutting problem, lack of aggregate structure.
It was throughout the whole...
No, just on the surface, on the
Surface friction course.
You're just on the surface friction course.
Doesn't rut.
This point is shoved aside. You see there? It's shoved aside. You see?
More like shoving of that surface.
Yes, that's shoving to the surface. Because that thing is... Okay, remember, I tell you again. That is not what you think an open grade is. That is open grade with an LA abrasion of 40. And maybe fines. So it's not really open.
I have a question.
Yes.
Don't you think high shear stresses the curves because of the...
For sure,
Yeah.
that's exactly it. The high shear stresses
Yeah.
where the tipping, maybe the same mix is the same all over, okay?
Right.
But the tipping point was the high shear stress, exactly.
Yeah.
Yes.
O Jorge, é importante colocar também que isso aconteceu em curvas de raio menor que 400.
Yeah, it's reminding me that these only happen on curves with the radius less than 345 meters.
Because of the high shear stresses.
Yes.
Yeah.
This was 22 kilometers long,
33.
33 kilometers long. What was there before was, you and I both know, quarter of all wrapped up in action. Horrible. Yes, that's it.
Yeah.
Trying to make this, or should be made. This is 15 years old.
Yes.
When we did this to begin with, we didn't know it was going to last 5 years. I mean, because of this LA thing, no, 5
Yeah.
years, 10 years, whatever. But notwithstanding these four little curves,
Yeah, few curves, yes.
this is a fantastic project. Right?
It is. Yes.
I think that's what should be brought to people's attention. Is the amount of savings here. This is now, to me, one of the perennial stretches of the roads I drove in Brazil. Tremendous performance. Maybe a little more should be made out of that, rather than, yes, there's something happening here that's still an anomaly. It's an anomaly.
Yes.
But by the same token, the whole road was built with this aggregate that we're
Yeah.
concerned about.
Yes.
This was brand new, everything. I mean, this, in some ways, this is not exactly what we had in mind. Because we were thinking of putting a sandy down. I don't remember that.
Mm-hmm.
But we didn't do it. Because
Yeah.
we had gone the aggregate.
Was not good. Yes.
Okay, well, he's listening to me, and that's the only thing that counts.
But it is why it's important to show that the structural performance is excellent. It improved.
Is anybody hearing me or not? I can't hear.
Hello?
Yes.
I'll let you say that. You hear me or not? And the main thing is, I didn't do anything.
You keep turning it off.
Does anybody hear me now?
Yes.
Right? Yes. Well, all I'm going to say is this was a great job, and we did fantastic work here, but we couldn't have done it without Angelo and all of his good work.
Yes.
And these little bitty rut things are an anomaly of 33 kilometers of a road that was horrible to begin with. Think of the savings. Think of the savings, as you showed in that one slide, right? Tremendous saving, right?
Oh yeah, huge savings. The alternative would cost much, much more. That's another paper where we already show this, okay?
Positively about this, notwithstanding the aggregate was,
Right.
but even that aggregate was on the entire project, right?
Exactly. The project was an entire project, yes.
So to me, this is a validation of what, it's exactly what Emil was talking about. Over and over again, we have evidence of tremendous success.
Yes.
And at times, maybe we dwell too much on the little things. This,
Okay.
to me, I think, is minor.
You want to have question?
Okay, can I?
Angelo wants.
Dos trevos e nas rotundas,
Sim.
que eu usei o gap, como o Jorge aí recomendou, não tive problema nenhum.
Sim. In any other place other than these curves, the whole job is perfect, okay? Anyway, so can I, and you need to tell Rosanna if you are going on Friday down to Algarve on the bus, because we want to make sure you have food for lunch when you get there. So please confirm who's going and how many are going.
The times, what?
No, good idea. The bus is going to leave at 7 here because the operation, the mixer, they stop working. It's because it's Friday. They stop working around 10 or 10:30, okay? So we need to go first to see the machine, the mix being made with reacted and activated rubber. Then we go see the job being made with it. Then we're going to see a 3-year-old job over, and I have a video for you tomorrow. And then we're going to have a great lunch, then we come back. So the time we come back depends on how long you're going to take to get lunch. So if you go very slow, it takes later.
Leave at 7.
We leave at 7. Bus leaves here at 7. The bus, the world is getting so strange, cannot park exactly in front of here. It's going to park in front of the place where we have lunch, okay? That parking lot there, that's where the bus is going to be. Friday. Thank you,
Thank you,
Angelo. It was a great job.
We have
Great
break
example.
now. Thank you, guys.
Doesn't work with George.
Can you hear?
A apresentação aí.
Okay, guys, let's start these. Let's get out of here.
Yes.
Pode botar na roupa que estava antes. Essa foto é a foto comercial. Qual é? Essa? Agora sair.
There's nobody here, but we have to do this. I hate to say it. That's what we have to do. We better round them up. That's great. I lost my schedule. All right, we're good. All right. Okay. All right.
Só vou ligar. Mic não.
Now the mic, yes.
Now the
MC the mic. Mike, the MC.
Good luck. Thank you.
Is it working or not? Push there. Okay. All right. Where did he go? Is he there?
They have to ring the bell. Yeah.
Oh, okay. All right. Okay.
I will ask George. So, to turn on?
That's all. Okay. Okay.
Do you know what MC means for?
What?
MC.
Master of ceremony. Yeah. Yeah. In case of George, it's a guy with a whip. You know, a whip hand. Now he's leaving.
Quer que toque?
All right. Yes. 6 o'clock. Yes, we have 6. That's right. Yeah. It's okay by me. No, I don't know if I get. No, no, yeah, I know, yeah, it is.
And you go by car?
I hope so. That's better for me. I haven't talked to him yet. I've had no time to talk to him yet.
Oh, okay.
But I also have to talk to Camille too. Are you ready? Are you ready? 'Cause we've been told by the boss to go. Close the door. All right. Well, to get them in here, get people in here too. Close the door. Get the flies out of here. We have to finish by 6. We have to finish by 6. We have to finish before we start.
Yes,
Sorry, we're already losing time already.
I just realized that we have a screen here.
Yeah, we have a screen. We're waiting to close the door here. And George.
I think there was one thing as a horn or something.
They're going to ring a bell or something,
No, I hear that.
or people are going to yell or scream or something. Don't worry, George is coming. Already, we're ready to go. Are we ready? Are we ready or not?
I know you gave me 45 minutes. Can you try to make me 30 because I'm not going to.
Sure, I'll squeeze it.
Squeeze it.
Yeah.
All right.
Start.
Okay. Welcome, everyone, and our speaker today, and we are very fortunate to have this gentleman, Xiaoping Yu, who I refer to affectionately as King Ping Yu, who I believe is worthy of being a king, for that matter. The name of his presentation is Implementation and Performance Evaluation of Large-Scale Rubberized Asphalt Project in Michigan. So just give him a big hand. The king.
All right. Good afternoon, ladies and gentlemen. Thank you so much. All right. Dr. George Susie actually told me I have 1 hour and 45 minutes.
Right.
I'm going to squeeze it a little bit. All right. So I'll flash. All right. So what I'm going to talk about really is a large scale. My large scale is compared to some really tiny scales.
All right, I'm not talking about the 33 kilometers long project, but I have some, decent size I'll show here. All right, so for those who don't really know where Michigan is, this is a map. You can see where Michigan is, the red color. It's really on the north side of U.S., and it's pretty cold, a lot of rainfall, and a really amazing amount of snow. Maybe sometimes you get a 10 meters snow a year, but not every year. All right, so anyway, this is where Michigan is. And over the years, Michigan generated a lot of tires, about 10 million tires every year, right? So that's pretty much where how much tires we generate. And most of the tires, of course, are not recycled for asphalt. They are. Some be landfilled, some be burnt for fuel, or make cement, or make electricity, and or some kind of illegal dumps, right? So those are what the current situation look like. In Michigan, though, so in recent years, we have really ramped up. We have been doing a lot of effort to recycle tires. So on this map, this is the Michigan map, you can see all the dots there. Those are the projects I involved in the construction, of course, design, construction, and evaluation. So those are some projects we have been doing. So far, Michigan alone, we have prepared about maybe more than 100 projects over the years. So total lane miles together is probably 400, close, maybe a little more than 500 lane miles. So that means, 640 kilometers lane miles, kilometers. Right, that is the current situation. And the next one, I'm going to show a few examples of case studies. We have a few places we build those projects. Some projects, I think they are really interesting, and I really want to show what that is about. So the first one, the project is Kalamazoo. This is Kalamazoo is the first. It's a place really where the COVID vaccine were born. That is a place, Kalamazoo. So in this project, it's a few miles long stretch. And we divided to several different sections. Of course, some are control sections, some are other sections. We also have, rubber asphalt sections, and also chip seal sections. So the chip seal really is pretty much similar like Arizona or did, and also California did in the rubber asphalt chip seal. So that's pretty much, that's the reason we have 4 different sections, all right, here. So I'm going to show you one section here, and on this picture here, you can see one gentleman here with a hat here. If you take a look at the room, if you see anybody wear a hat here, this is a handsome guy. All right, so now the hat is gone. So this guy, I work with this gentleman here, Dr. George Souza, right? So we work in this project. This is very one of the first project we attempt use a really high content of rubber materials. All right, so this is the dry process. This is the first one project we tried it, and the construction, everything was fine. Okay, so we use a really cheap binder, the asphalt binder. The cheapest one we find was PG 5828 binder, and then of course with about 24% of the rubber from the product. So eventually, we make the rubber asphalt over here. So this was a pretty interesting product, very successful. There was a video here, of course, we don't really want to show too much about it. So I only have 1 hour, 45 minutes. All right, I'm going to flash. So one of the interesting things was, we did some lab work here. Even though a lot of technology has been proved, however, it's not really being delivered to a lot of areas. So we have to really show people. All right. So with the equipment we have, we do a test called the DCT testing, which is called the disc-shaped compact test. This test is, the sample is over here on the right-hand side. But if you did not see those things. This test is very popular in a lot of northern regions in Michigan. In U.S. So especially like Minnesota, they use this one as one of their criteria for low temperature cracking controls. So for this graph here, really my point here is trying to show you what's the difference on resistance, right? So we call fracture energy. So pretty much the rubber asphalt, they get really high fracture energy resistance. That's really good for us. That's the reason, and we are using rubber asphalt, for this particular project here. And there are a lot of data. I'm not going to show all those kind of things here. Basically, what I wanted to show you also is about the rotting resistance. We use the Hamburg wheel testing. We measure all those things. So pretty much rubber asphalt, we have a lot of unique performance, right? The resistance is good, so that's something we did. And also we measure the flexure fatigue. So basically trying to find out the fatigue life. So the control asphalt, which is the gray bar in the front, you see it's pretty low, but the rubber asphalt is pretty decent, right? Very good. So there are several magnitude higher. So that's really good, right? So that's to give us pretty much confidence, about the materials we're using. Of course, the other thing is about the noise level testing. We only read the first 2 bars, okay, for each of the groups, because that is rubber asphalt mixtures. You can see these are, consistently the green one. The first one is rubber asphalt. The second one is a regular one, which is, both are new road. For example, like the 40 miles per hour speed, which is 64 kilometers per hour. You see 72 versus 74, 75 or so. So it's about maybe 3 decibel points of differences. That really means the road is quieter, right? So at this speed. So this is one question we discussed with Dr. George Souza. And that time there were not many Tesla available. And he encouraged me, find a Tesla, drive on it. Let's find out what the noise reduction quality look like. All right, so anyway, eventually we did not get a Tesla. We got a diesel truck, but that's okay. All right, so what my point here is, there are a lot of really good, good performance. So we find out here. So pretty much verified that crack resistance at a low temperature situation is really good. So it's, you get, very good fracture energy resistance and a very good fatigue resistance. And 50 times better, right? That's and of course the other thing is about the noise level. So the noise level has been improved quite a bit, right? So on average, about 2.5 decibel points, but so some cases, 4 or 2, about those ranges. All right. So the rotting resistance also good. So what else you want, right? That's pretty good, right? That's pretty good. That is the first project we did in Kalamazoo. After the success of Kalamazoo project, we did more and more. So the second project I wanted to show you here is Dickinson County. Where Dickinson County is, if you take a look at the map here, I'm going to show you where the map is again. All right, sorry, I have to come back to the map. The Dickinson County is right over here. All right, almost on the tip of this, the upper peninsula, this portion here. So very cold region. All right, so very cold. What I'm going to show you here is on this cold region, we did was, we are trying to actually, or here, sorry, this is actually Bay County by some reason. All right, so this is the place, all right. So you can see in Michigan, this land in Michigan, this land in Michigan, it's pretty much surrounded by 4 Great Lakes. So that's what we call Great Lakes area. That's pretty much mean, Michigan is one of the really centers here. So this is the project we have here. It's called the 6 miles road. A total is 6 miles stretch as control section and about 2.3 miles as our rubber asphalt sections. So this road was in a pretty bad situation. I'm going to show you how bad it is just in a few minutes. So what we designed here, the underneath was concrete pavements was over 100 years old. There are, of course, they patched a few times, and then they add asphalt on the top, over the years. So now you see bigger cracks happening. So it's a very bumpy road. This road called Dixie Highway. For some people really in U.S., they know this is a Dixie Highway road. It's very famous, right? Because from here, this road you can go all the way to Miami, Florida. Anyway, the 2 details about history, I really don't want to talk too much, but really the pavement surface is bad. So eventually what we designed was we are going to use a rubber asphalt chip seal, as a semi layer. So a semi layer, and then on the top we put a 2 layer of rubber asphalt. All right, so what happened here is rubber asphalt on top, of course, to prevent the crack happening, we also pre-cut the asphalt portion on the top, according to the joints level. So anyway, that was something we tried it. And also the rubber, well, before we put the rubber asphalt here, of course, we purchased a cheap regular binder. The asphalt we bought was PG5228, which it was very cheap. All right, I can tell, very cheap. You usually don't really use this asphalt in anywhere, roughly. All right, pretty much you don't use it. So anyway, here's what the condition look like. It's very bad, right? Very bad. So here is what we did. Okay, so first we need to mill a little bit off. Okay, it's roughly about we milled a 2-inch, so about 5 centimeters, materials off. Right, so we mill it, and then we have rubber asphalt materials. Apply on it. This is hard rubber asphalt, not emulsions, not emulsions. So then with that one, and then you apply chips. This is the exact same thing like Dr. Susie and I did in Kalamazoo for a different sectional project. So this one, of course, this is the material here is a raw material. It's just the rubber strip that get from tires. All right, so without any process, without surface treatment or without anything, of course, we have to cook this one longer time. So after that one, the project is, it's, cleaned up, and then this assembly layer is kind of ready, right? It's kind of ready, you clean up. And then, of course, we place on, of course, this is how they prepared the materials here. So how they really prepare the, from the PG5228, and how to really modify with rubber materials. So then, of course, with the high content rubber materials for here, roughly here is a 22% by weight for the binder. So it's pretty high content here. And of course, the temperature used here was, pretty decent temperature, very decent. All right, here is when the rubber asphalt prepared. Of course, this is the wet process. The previous project I mentioned to you, that was actually the dry process project. Here's the wet one. So this wet one, so because of 2 layers, all right, so they get the first layer on, and of course, after that one, we get a wearing course, same process. But the good thing for this project was the 2 layers that we use same asphalt materials. Of course, we also have the other 6 miles of roads. Those are the control materials we are using. Those are using DOT's standard mix design. All right, here is what the construction process look like. You can see this is what, they are spraying tack coat. This tack coat has to be emulsions for this case. Of course, we eventually, we construct this one, the middle 2 lanes, and also then just construct the outer 2 lanes. This is a total of the 4-lane roads. So anyway, you can see this was the construction site, and in 2024. Of course, after the compaction, after finish the construction, things looking pretty good. We did a lot of lab work, okay, trying to re-verify a lot of things here. And I'm going to just maybe skip these things, okay? So we test a bunch of things like DSR, RAR, after the aging, after long-term aging, what's the performance look like, all right, just to re-verify, what the new PG should be, right? So that is, of course, we also, for the mixture testing, we test a lot of Hamburg wheel testing machines. We run about the APA testing, all kinds of, diagnosis we have. All right. Anyway, so we also tested our favorite testing called the DCT here again. We just, of course, we also test ideal CT. That's another thing, people are using. But really what my point here is, the resistance of, cracking resistance is get pretty good, right? So this one is get 4.4 times better than the regular materials. And of course, we test a bunch of other things like dynamic modules, because in the design, we have a component here was trying to do a pseudo mechanical empirical design. We have that one in our mind. We think this road is going to be a perpetual pavement anyway. All right, it's because the foundation was good, old concrete, even though it's 100 years old. There are some decent asphalt layer on the top. Then plus this 2 layers of new asphalt should be lasted for a long time. Right, let's see what happened next. And I'm going to show next one here is, okay, we also have some kind of testing, we'll call tensile strength ratio testing. I saw there are quite a few testing results shown here, but anyway, my result here is shows that one, no matter which design we have, according to all the DOT specifications, TSR is okay. So with a tensile strength ratio, it's passing all the specifications. And this is after 1 year, winter traffic, everything like that one, this is the regular control sections. Things, of course, it's a new road, okay? I don't think this should break, should have any problems. So this is the regular one, and the next one is a rubber asphalt. Because we take picture under special light conditions, early morning, so that there are some kind of does not look really dark, but it's pretty dark, right? I mean the road's color because of the rubber materials in it. All right, so let's summarize this project in this project here. It's a 6 miles of control asphalt, 2.3 miles of rubber asphalt. So the total rubber asphalt we're using here was 17,000 tons. So that's probably marked as one of the largest projects ever in Michigan. All right, so that's the reason I said large. But of course, compared to some project we have, it's not really that big. All right, so we should be okay. So this is all the things. Of course, the project is wet processing. And crack resistance improved, moisture resistance is good, rotting resistance is good, fatigue life is good. So that's the construction was smooth. Of course, we have some kind of we learned a lot of things along the way, but in general, it's a pretty good experience. That is my second project I want to show you. This place, it was also relatively cold, but not as cold as where our other project I'm going to show you. So this project is called Dixon County project. I'm going to show you where Dixon County is. Dixon County is over here. You see this is the Upper Peninsula portion. This is the lower Michigan part, but it's right here. So it's pretty cold here. So this road called the County Road 573. It's a cold roads, old roads also. It's connecting the mines and the logging directions. So a lot of logging trucks, mine trucks. There is a called Pacer rating. That means how bad the road is. From 1 to 10, that's range. About 5 usually are okay. 10 is best. 9 is pretty decent. Under 4, 3 is horrible. So this rating was a 2. That means really bad. So we're ready for construction-wise. You probably need to do a reconstruction. But of course, the problem is, if you need at least $2.2 million to $4 million budget, they don't have that money. So what did they do? They just talked to me. I said, okay, we have a cheaper way to do it. Do you want to try it? They see the data we have. They said, okay, let's do it. So what we did was, using dry process approach, 20% of rubber content for the, by the weight of the binder. So we did the project, and the budget was controlled within $1 million. All right, so it's a pretty long stretch road. I'm going to show you this one. You see this what the road look like. All right, the road here was, this road was built in 1989, never touched it. And the other piece road, of course, it connected, and that one is built was in 1993, never touched it. So pretty much, long time, right? Long time, no much work done, and it's cracked like that. So it's pretty, very, I'll say, very bumpy roads for logging trucks, mining trucks use. All right, so that is, of course, I have a video here, but we probably don't have time to show those things. We can just let it escape, I guess. All right. So of course we did things. We did a lot of lab work as well. So the binder we are picking up, we test all the binder, but the properties. If you take a look at on the right-hand side, this is the rubber modified asphalt with 20% of rubber in it. So the binder really get improved quite a bit. And so it's pretty much, you see the temperature is bumped about 20, almost 20 degrees C, right? So on the rotting resistance side. So that's really very good. But of course, we have a lot of data showing you what the actual PG look like. Okay, I have enough data showing those things. I'm going to show you maybe something. For example, we also tested one thing called asphalt binder crack device testing. It's basically trying to see what is the crack, at what temperature the asphalt binder will start to crack. So the conventional asphalt will crack like -40 or so. This is a fresh asphalt, not aged. And then the other one, after they make rubber asphalt, you can see it's cracked like -50 degrees C. That is really give us, quite some confidence. So this is, one of those testing. We just want to show you what the performance look like. The agency love to see these results because with the limited budget, the road condition, original condition was look like that. So it's really hard to do the project without really sufficient budget. All right, so what we did was we also trying to mix the mix design, all right, just to help them to get the design ready. And we measure all the rotting performance and measure the fracture resistance. And of course, the fracture resistance was, improved quite a bit. For example, here, the 500 joule per square meter, we can improve that one to like 650 or so, right? That's one of the results I want to really show you. And the rotting resistance also get improved. And here's before the construction, the road was looking really very, bad. But after construction, you see it's pretty decent, right? Well, this is the U.S. Of course, the center line always yellow, right? It means don't go through. All right, don't pass. All right, here is also we showed the noise level. This new road, right? This is a new road on the left hand, the red, those bars. That's and then of course the newer roads pretty much get quieter on the noise level. Right, that is Kalamazoo, Saginaw, Dixon. All right, those are 3 projects. I'm going to show you one more project. So the first one was a dry process. The second one was a wet process one. And then the dry again. And on the Bay County one, this one is also another simulator project. This simulator has been almost 5 years. That's the reason I really want to show that one here. This one is not really, this one I think a project we work with the Liberty tires. Here, Liberty tires, the dog here? All right, great. All right, if you're not here, I'm not going to talk about it. All right, this road is, we call 7-mile roads. We got a lot of control sections. We got enough control sections. Control sections was almost 8 kilometers long, right? Different stretches. Well, on the same road, just many segments. And on the rubber asphalt, we did was 3.4 kilometers long. And of course, with other rubber, with 3.09 kilometers, is another kind of wax product. So we can ignore those things. So my point here is just really want to show you. This project is similar like the Dickinson County one. This one also really needs sort of reconstruction. But of course, the condition was not as bad. This condition, I would say that we called PACER rating, probably I would say is maybe 5. So it's okay, not too terrible, but of course, it's need to be fixed. So reconstruction will use a lot of money. So eventually what we did was, without even milling, we just used a rubber asphalt chip seal as a semi-layer, and on the top, just 1 layer of rubber asphalt. Of course, that is how simple we did. And this is what the plant look like. This is a mix of hot rubber asphalt. And of course, this is dry process. And this is what the field construction look like. Spray hot rubber asphalt, and then apply chips and roller chips, make sure they are embedded inside. And of course, after that one, we go pave the surface course, rubber asphalt, and continue the surface course. And after work is ready, if you take a look at the picture here, they're all black. All right, so that is just 5 seconds to show of what's the project construction look like. And here are the results. I want to show you a few things about the results. But of course, you can see we did the DCT test again, disc shaped compaction testing, trying to find out what is fracture resistance look like. I think the data here is very crowded, but really I can guarantee that is all the rubber asphalt performance are way better than the regular asphalt, right? So because the fracture resistance was good. And also I want to have on site showing what really the actual energy resistance look like. And I think on the left-hand side, this one, all the first bars, this one is conventional, this is conventional, this one's conventional, but the rubber asphalt, you see they almost double the fracture resistance. That means that's really good, right? So that's, that really means the road is not likely going to crack or very difficult to get a crack. I have results, I want to prove that one. All right, we also tested about rutting, and I'm going to skip this one for now. And we test all the noise levels. So, for all the rubber asphalt we see, it's pretty much, even at different test speed, usually the rubber asphalt, they are quieter compared with the new conventional asphalt materials. All right, so that's the noise level. And I wanted to show you a few things about the after actually right now it's 4 years data. All right, here is this one, this column here is what? Is a control asphalt, right? Control asphalt with SAMI. This one here is control asphalt without SAMI, all right, without SAMI. And of course, rubber asphalt, so with SAMI, all right. So what I'm going to show you here, so let's take a look at the lot, this one here. So after year 1, new roads, without rubber, without everything, so, you got some, starting to show the crack, right? Starting to show the cracks. Of course, the severe level is not too bad, okay? So, roughly about 6 meters or so, you see one crack, right? Because the existing condition, there are a lot of cracks, right? So it's about 5-6 meters, you see cracks. And after year 2, you see about maybe every 2 meters, you see cracks. And then right now, after 4 years, you see probably almost the half meters, less than half meter, you see crack. But take a look at all the rubber materials we have here. It's 0, 0, 0, 0, no cracks in the first 3 years. And then starting this year, last winter, it slowly show a little tiny bit of hairline cracks. I still want to document it here. It's more than 2 meters long, of course. That means there are not really huge amount of cracks. And the hairline size, very tiny. So I don't really think that's going to be something really cause you concern. But at least this one, that means after 4 years, you slowly see something. Somebody can make you younger than 4 years. That's something really interesting. All right, I'm going to go to the next one. So next one, I really just very briefly talk about some of the environmental effect research work we are doing. And I want to really briefly do that one. George, do I still have 5 minutes?
Yes, you do. You have 5 minutes.
All right. So here, I also been tasked by public and also the agencies talking about how about the potential hazard in tires. So I was asked to do some research on it. So what we did here was trying to search what is the 6 ppd chrome. What's that stuff look like? People are saying this one is kill the SAMI, right? So I talked to my department there. I mean our government, right? Our government. They said our SAMI live better with tires by some reason. All right. So anyway, we did the research. We tracked it. We measured those things. And we measure. There are some kind of things we detected on the control asphalt, regular mixtures. We don't see any 6 ppd, but in the rubber asphalt. This is rubber asphalt. We see some kind of detections. The number, you can see those things. However, those numbers are actually still within the limit, put up by the government. We also search how much copper, how much sulfates we have in the groundwater, right? So after heavy rain, we collect those water samples from roadside and, regularly and trying to check those things. Of course, one thing is, of course, we always trying to check those things. And eventually, of course, those things are still really way below the standard we have seen. Because here you see the unit here is nanogram per liter. The requirements, well, the limit was 90, what's that? It's 0.095 milligram per liter. So anyways, that still means we are still, not that range yet. But of course, we are searching more things here. You see, I also checked another project we did was in this one, instead of on the roads, we are actually we have construct project with the TDA, tire derived aggregates. So this project, of course, we also measure all those things here. You can see we measured the things about zinc, iron, magnesium, and copper, all those things. eventually, whatever you find out as, although the leaching potential was still lower than some kind of a suggested maximum value. So, of course, this is not the end, all right? We are, in the very beginning of the measurement of this type of data. And another type of project we are doing, just starting this year, we are actually bundle the tire chips together and like one big block. We are using this kind of block to hope this material can treat the water, storm water, so it can remove the contaminants because the surface area for those chips are really large. So there maybe is a potential can be used as a filter. So this is a research work ongoing, and it looks like you see this big block here. There's roughly about 1 ton, right? And it's pretty heavy. So we have to use equipment to lay down those things. But right now, the initial study shows that this one is very effective. But of course, we are still doing work on those things. So this is probably about 1 meter tall, right? So pretty, pretty big size materials here. All right, so as a summary, very briefly talk about some summary here. Here is one thing I just talk about a few projects here. You see the Kalamazoo project, roughly the rubber content of 24% by the mass of binder, and the Saginaw County about 22%, and Dixon County is about 20% for the binder. And Bay County actually is combined all the rubber asphalt chip seal and their top lift of materials, roughly equivalent to about 18%. So of course, most of the project we did in the state is roughly about 10% of content. So we are doing probably a lot of those things. You can see really the second project probably is the largest number, 17,000 tons of rubber asphalt being placed, which is equivalent to about 54,000 tires. So that is a project I wanted to show you here. So this is a summary of the work. And we are still trying to do some work here. So I'm glad to see there are a lot of research work trying to do on the Environmental Product Declaration, EPD. This is something what we are doing. So we are teaming with state agencies and local governments, trying to make sure whatever the EPD we have here is within a relative, narrow limit. That means we want really to have those numbers are below 50% of the entire country's number on the initial EPD. All right. So with that one, looks like we are right now, I think one big project we're dealing with is I'm being asked to write the specifications for the state. So that's the reason in the last day or two, right now I'm talking to different people, asking their opinions what we do with the specifications. So one specification is rubber asphalt chip seal. The other is rubber asphalt mixtures. So that's something what I'm working on now. So if you receive an email request from me or from my colleagues, please don't be shy to help us. We want really your input, right, to make the rubber being applied, more in more locations, right? This is a few pictures, of our work being recognized by local governments, agencies, and also this one you see this project. This gentleman here. We worked together on this project. We also won an award. I should let you have this one also. All right, we have a lot of people supported us, a lot of agencies. This is our incomplete list, all right? With that, thank you so much.
Thank you. Very well done, and really on time. I don't know if I should ask for a question or not. I don't think so. They can ask questions at the dinner.
Sure, I will be happy to be asked.
I think we will move right along because otherwise George is going to beat me later. So our next speaker is Mata Parthi, I believe. It's pretty close anyway. And his subject's going to be warm mix asphalt rubber compactability metrics optimization of production and compaction temperature.
Good evening, everyone. Thank you very much for being here, and special thanks to the organizing committee for this opportunity. My name is Sri Gangadhar Mattapati, and I'm a PhD student from Indian Institute of Technology, Tirupati. I'm here with my Professor Krishna Prapunna Biligiri to present our research work titled Warm Mix Asphalt Rubber Compatibility Matrix, which is an attempt towards optimization of production and compaction temperatures of asphalt rubber pavements. As you may recall from the today's keynote lecture from Professor Krishna Prapunna, where he mentioned certain set of R's that help transform the linear economy to a circular economy. Let us apply those R's to the asphalt technology, such as recover and recycle, where you recover the rubber component from the end-of-life tires, and you get the different sizes of rubber particles, where the fine particles can be blended with asphalt binder to remanufacture into a binder known as asphalt rubber, which can be reused into pavements that have higher resistance and perform well in all road, all weather conditions. But the major issue with the asphalt rubber pavements is the higher viscosity at higher temperatures, which will have higher production temperatures. So we need to reduce and rethink this technology with the use of certain type of additives known as warm mix asphalt additives, such as organic, chemical, foaming additives, which reduce the temperature of the asphalt rubber pavements. For the unmodified binders, we can find the mixing and compaction temperatures using the ASTM, AVTS temperature susceptibility relationships. Whereas for the modified binders, such as asphalt rubber binders, these methods are not applicable, since viscosity depends not just on the temperature but also on the applied shear rate. Hence, we need to come up with a practical method that can be used at the laboratory level that can show the true mixing and compaction temperatures applicable. So we are proposing a mixture-based methods along with the warm mix technologies that can be applied. Hence, the objective of our research is to evaluate the effectiveness of mixture compatibility matrix of warm mix asphalt rubber mixtures prepared with 2 warm mix asphalt additives, and finally to know about the production and compaction temperatures and compare the reduction potential. The scope included preparation of AR binders and mixed design to find out the optimum asphalt content that is required, and finally the proposed method, that is asphalt mix compatibility test method, to compare the reduction potential of the warm mix additives in warm mix asphalt rubber mixtures. As you can see, the asphalt binder that was used was viscosity graded VG30 binder and the crumb rubber of mesh size 30. It was blended with the local quarry aggregates that are obtained near our place. Regarding the warm mix asphalt additives, the 2 warm mix asphalt additives that were used were asphomine, which is commonly used in the European nation, where it contains about 21% of the water content in its structure, which will be released into the asphalt binder when heated in the temperature range. So one more additive that we developed indigenously at our IIT Tirupati is from the fly ash, where you collect the raw fly ash and calcinate it at a higher temperature that becomes reactive, and then you hydrolyze it for a certain time and temperature that can have 16% of water content in it, that will help form the asphalt binders. So using these, first we prepared the asphalt rubber binder, where the virgin binder was heated to a higher temperature and then mixed with 15 and 20% of by weight of bitumen, and sheared at 1000 RPM for 90 minutes, where we get the AR15 and AR20 binder. 15 and 20 represent the rubber content in the respective binders. Then the binders are subjected to fundamental consistency tests such as penetration, softening point, and viscosity to know about the mixing and compaction temperatures using the conventional method. And then we proposed the mixture method. So for that, we have adopted the Arizona DOT gap gradation, and the mix design was superpave mix design. We limited the mixing temperature to 175 based on the Asphalt Institute recommendations, and the optimum content, asphalt content, was based on the air voids between 3 to 5%. So the methodology is that we prepare the control AR mixture at the 175 and 160, and then the Warmix asphalt rubber mixtures were compacted at 3 different compaction temperatures, and the variation of air voids with compaction temperature was plotted to match the air voids content that give the same performance. As you can see, based on the consistency test, the AR20 binder has low viscosity temperature susceptibility, which means it performs very better. If you calculate the standard equiviscous approach, the mixing and compaction temperatures, you can see there is a jump of about 40 degrees Celsius from the virgin binder to the AR20 binder. So if you heat the AR binder at such high temperatures, obviously there will be a lot of smoking effect, and then the binder may lose its elasticity properties. So the mix design that was adopted gave us a optimum asphalt content of 5.8% for the AR15 gap graded mixtures and 6.2% for the AR20 gap graded mixtures. So this method that we followed gave about 12 degrees Celsius reduction with the fly ash additive that we used, and the asphomine additive that is commercially available gave us about 23 degrees Celsius reduction, which is in line with the supply's recommendation that it can reduce a temperature of about 20 to 40 degrees Celsius. So that we can achieve with this method in the laboratory, which is not possible with the viscosity-based methods. Hence, the proposed method is reliable to know about the metrics of Warmix asphalt rubber mixtures. Similarly, for AR20 binder, the fly ash zeolite gave about 11 degrees Celsius reduction, whereas the asphomine gave about 17 degrees reduction. As you can see, the foaming effect that was observed with the asphalt binder when we added the zeolite, there is a water that is foaming, and this helped reduce the viscosity temporarily and then production temperatures as well. So the asphalt mix compatibility test that was proposed was well effective and practical to capture the temperature reduction potential when we use the foaming additives. One more key takeaway from this research is that the fly ash additive that was developed contribute to the circular economy through the valorization of fly ash waste. Moreover, the reduction potential that was observed is in line with the reductions claimed by the supplier, and hence this proposed method at the laboratory level is more reliable and representative tool. Further, we need to access different Warmix asphalt additives, dosages to develop this method in future. So I would like to acknowledge Anusandhan National Research Foundation from Government of India that helped travel research for our thing. And you can scan this QR and to know about our research group. We are always welcome to collaborate. Thank you very much.
And thank you. We have time for a question because our next speaker, and somebody in the back there should go out and get our next speaker because he's not here. Is he here now? Well, then get the hell up here. Thank you very much. Great presentation.
Thanks.
Our last speaker, who almost didn't make it, is somebody nobody knows who he is. But this is a integration of recycled tire rubber pavements and solar energy, a novel concept.
Okay, I'm going to go really fast because I want you to get out of here and go have a gin and tonic. So basically, the idea is we are very worried about making sure we recycle tires, we save the energy, less CO2, but we have roads, and the roads are under control of the government. So what about to put solar panels over the roads so that we have less sun on the roads and less moisture? So we save on aging and we save on moisture damage. Therefore, with rubber, which we already know is very good at resisting on this, resist rotting, I'm not going to repeat this, it's well known, and we have all these benefits. But now, why don't we bring the sun into it? Because everything with the sun is less CO2, less damage. Just take advantage of the energy provided by the sun. So let's make sure we combine both. So very quickly, to make sure we really have a resilient, sustainable society, how about this? Very simple. We have rubber roads, and we have solar panels over the roads. What's wrong with the idea? Look, the damage on the road, it decreases tremendously. No sun, no UV damage. No water, no moisture damage. So the pavement is going to last twice as long, for sure. Now look at the sun in US. This is a case we studied, actually, he did it. More sun, more radiation, all that. Someone, 2020, showed that if we have an area in Arizona that covers that amount, is sufficient to provide all the electrical demand in the US. Okay, so based on it, you got the idea. Okay, for sure, there's more surface area covered by roads than that little rectangular there. Anyway, some people had a similar idea, and they decided to put the solar panels on the road. What do you think is going to happen? Okay, it's obvious. Concrete that's broken by trucks. So, do you think a little plastic, something on top is going to resist? So they put these, obviously it got damaged. So you can have very creative ideas. I like the one on the bottom left. Very beautiful here. But you know, you can save more money, less money. Be creative like this. And in the end, look at this. You have a lane that your car with induction keeps driving over and recharges. Obviously, some software AI bills you for it, but it's possible. So in red, there's the roads, left to right, that can be very easy to convert into solar roads. Actually, China are starting to think about this, roofing highways with solar panels in 2024, and they are considering this is a possibility. I don't know if they already start doing it, but at least there's a paper with it. And the amounts are amazing, the amounts you can generate of electricity with that. So, you know, now combining both, you have the benefit of the roads and the benefit of no sun and no moisture on the roads. So very quickly, that's it. Just a crazy idea. Bye-bye. See you in Alfoz. Go there. Uber by car. Be there before sunset. Sunset today is at 7. Be there at 6:45 so that you can have a drink toasting to the sun. Out of here. Go, go, go.
All right. Very good. Very good. You made it. We're done. You're going with aluminum. I'm hoping to go with